Okay, well, thank you all for joining us. We are very pleased to have Vlasta Sikimić joining us today to talk about the use of AI in scientific evaluation. Vlasta, take it away.
Thank you so much for having me, and big thanks to all the attendees, because I noticed some of the familiar faces, and I'm very grateful that you took your time to listen to my talk. I will talk about the use of AI in scientific evaluation, and in particular, when we think about predicting scientific success, we know that this is a very hard task, and it's not very easy to see which projects will be successful. So to start on a funny note, we can think about the fortune telling, or looking to a crystal ball to see whether our research will be impactful, but we can also do something better, and that's use the algorithmic grant review. There are different types of the potential use of AI in scientific evaluation. One that's already been applied is for finding the reviewers optimal for a certain project, then also for predicting fruitful research topics. And some funding agencies are consulting algorithms in order to determine which topics to fund. But what we will in this talk mainly focus on is identifying optimal team composition, and based on that, making the predictive models for grant evaluation. When we use data-driven techniques of such sort, apart from the potential of using it for predicting the scientific research, we can give instructful insights in how to optimally structure research teams in science. We will also reflect upon ethical and epistemic considerations related to automated grant review, and in the end mention different potential ways of doing algorithmic grant review. The key questions that we will tackle are: can we reliably use AI in grant review? And that is the epistemic question. And the ethical question, okay, under the premise that we can do it, should we do it? And the motivation behind why someone should entertain the idea of using the algorithmic grant review is that the standard peer review has been criticized as time-consuming and costly. So researchers need to spend significant amount of time on reviewing the grants, which also costs money and takes them away from their usual research. And even this process has been criticized sometimes as unreliable. The peer review methods have in the literature been criticized as unreliable even when it comes to the paper peer review. But an additional component in the grant peer review is that we don't make it blind. So the reviewers actually know who is evaluating them, and that can cause different types of biases. Moreover, we are evaluating also the profiles of researchers, so we really check their CVs and in details, and that can have either explicit or implicit biases, because humans are prone to that. In addition, certain cytometric studies have been done, and they were they were trying to establish the correlations between the rank of the assigned projects, so the projects that got funded, so how they were evaluated and ranked by the reviewers, and how successful they were later. The correlations were very weak, meaning that the authors who conducted this research assumed that this is not very reliable. For all these reasons, a lottery approach has been proposed for assigning grants. And the idea there is that it's much quicker and that it can reduce biases that humans would have. And it also, because if we start with the premise that predicting scientific success is very hard, then we are as well as good to go with the lottery. Of course, there are more fine-grained approaches when it comes to the lottery assignment of grants, and that's that all projects have to pass a certain threshold, and once they are so good, so once they've passed the first evaluation phase, only then we can apply the lottery approach. But the same objection still holds, because we can still see, okay, but then it's again the randomness, a certain random assignment among these top projects that were pre-selected. The peer review, the algorithmic grant review can most likely do better than the lottery approach. But on the other hand, it's really questionable how well it performs in comparison to humans. We know that machine learning has already been used for pre-screening of job applications in industry, and that is considered to be a very efficient method for pre-screening, and it's not as arbitrary as just picking the first half of applications to be considered. It is also a fast and cheap method. And, you know, just to give you a flavor, when you get too many applications in industry, then one gets overwhelmed. And there are these examples and considerations that some people are just excluded because they just didn't have enough time to process their applications. And this is considered to be a fast and cheap method, but we wonder, okay, how reliably can it predict scientific success? And the answer to that will strongly depend on the data that we are using for these algorithms. So which data we consider relevant for the scientific success. Some ideas of which data we can consider is that we can wonder whether the different number of researchers on a project or different project structures might influence the scientific success of a project, or patterns of how they are connected in the sub-teams, teams, and so forth, or how long a project will last. Those are all options that we can think of that could be relevant parameters for determining scientific success. To start with the case study that is presented in the paper that my colleague Sandra Radovanović and I recently published in the European Journal for Philosophy of Science, we focused on the data from the high energy physics laboratory Fermilab and wondered whether we can algorithmically predict scientific success of the projects there. Why we chose Fermilab? Because it is one of the biggest and most successful physics laboratories. We also chose physics because it's a relatively reliable, because the field follows relatively strict patterns of convergence to the truth. And more importantly, we had at hand a well-established data repository in which we could see what is exactly happening with the data in physics and how physicists classify their success themselves. And that was important for us because if one is not careful with all these metrics, the results won't be informative. What happened there is that we selected 67 experiments or projects that got funding to be run in Fermilab, and we first conducted a qualitative analysis of these projects to determine whether they are comparable with each other. Then we used the data that was available at the Inspire platform, which is carefully curated by physicists, to determine the efficient experiments, and only after determining efficient experiments on this data set we trained the predictive algorithms and got an interesting result that the predictive analysis has shown moderately high accuracy, meaning that we are actually measuring something informative using these methods. How the whole methodology looked. So we use data from the projects. We first estimate the project efficiencies. Already this first phase will tell us something about the structures of research projects. Then we divide the data on the training set and on the set in which and on this training set, we are making running the predictive algorithms, and then in order to determine the accuracies, we compare the training set with the remaining set to see whether the predictions will be accurate and see that there is a moderately high accuracy indeed. Now the juicy part. So which data were available? Are these data satisfactory? What exactly this data is tracking? The data available were time, so the duration of a project, number of researchers, and number of teams or sub-teams within a project. And it would be there also interesting, of course, to include parameters such as funding. However, that was not available. One should keep in mind that some data we can consider as informative for the scientific success, but some other data will most likely not track it. So there it is really crucial which data we use and which data we choose to use. And we also, as outputs, used paper categorized by citations. This means that there were 6 different outputs because papers were ranked in different categories as known, well-known, less known, and so forth. And these categories were given by the researchers. And in each of these categories, we knew how many publications each project had. There, it was also very important only to use projects that finished in the past so that there was enough time for all the citations to come with respect to these papers. The method that my co-author used was a data envelopment analysis, because that is an algorithm that optimizes over all input and output parameters and gives us the efficiency scores. There are also different candidates for this algorithm, but for methodological reasons, we believe that the one that takes into account all of these scores and finds the optimum over all of them should be the best one. And then the predictive algorithms were later used to estimate the efficiencies, but only based on the input values. So what it means, that one could get a project proposal just stating how long the project should last, what is the structure of a project, and that we can in a way estimate how successful this project will be with respect to the citations. When we started this project, we did not know that results will be, how accurate the results will be. So it was a pleasant surprise that actually this was tracking something. But before that, another caveat that was really important, that we consider that we can only compare experiments that are similar. So certain experiments have far more citations because, for instance, it's more predictable. So certain precision measurement or a calibration of an instrument, calibration of instruments are really highly cited because everybody who uses the instrument will cite the paper reflecting on what was done to calibrate it and so forth. And you immediately see, so in order to do that, there is this qualitative path that you really see what's happening within these projects. But if you also just run the brute force analysis on them, you will see whether something is an outlier, and then you can again qualitatively consider why was this an outlier? So why is this project so different from the others? As a result, we obtained the list of efficient projects, which is also insightful with respect to how to optimize team structures. And we also obtained a list of inefficient projects that we could learn how to improve with respect to each variable. And already there, we got some reactions from physicists, and they commented on one specific project saying, no wonder that our project is ranked as inefficient. When I was working on it, I had a feeling that this panic was sinking. So actually there is certain tracking, but you can already anticipate that there is a certain privacy problem when you are marking certain projects as inefficient. So that can influence one's career, and one should be very careful with that. The last thing that I already told you, that the predictions had relatively high accuracy, and that is of our interest The tendencies with regard to the team structure is that smaller teams outperformed big ones. Especially, it was the strong result was that the projects that had less sub-teams were more successful, and this actually makes sense. And when I talk about sub-teams, I mean the institutions participating in one project. So the number of institutions participating in one project, these projects are in general rather large. And this makes sense because coordinating a large collaboration is much harder than just having a smaller collaboration. But one should keep in mind that some projects require large collaborations, and we have this tendency in physics. And these projects are also treated by people assigning funding as outliers. So the decisions about their funding is also done differently than the standard ways in how this is done with this large amount of application data that usually grant proposals receive. The predictive analysis gives us these heat maps where blue is marking efficient projects and red inefficient projects. And we are seeing that there are certain tendencies, so certain saturation with respect to the time when the project will be efficient. And if the project lasts too long, that it just might not be any more fruitful, so that there might be some sunk cost bias why people are still invested in a project that didn't give over a certain time span good results. This is very interesting. So once a funding body, for instance, that would run an algorithmic grant review gets these heat maps, then they could already know which projects and how to create a project that will be successful. And that is, there we immediately see the problem of some adversarial behavior, that certain researchers might just try to make their projects fit the certain parameters and criteria in order to get funding without really focusing on the substance of the project proposal. And this issue can technically has a certain technical solution, and that's to increase the amount of data gradually, which would also shift all the time these heat maps. But on the other hand, it's also not such a bad type of investigation if the only goal is to optimize the project. So for people that are really motivated, that are not having an adversarial behavior, but want to structure the optimal project and a good project in their field, this could be informative because it can also tell them what to look for. It can maybe also tell them when to drop a project that didn't give results until now. Again, all keeping in mind this first picture that we had, that predicting scientific success is a really hard task. So there will always be certain outliers. The other big limitation that we already mentioned briefly is the limitation with respect to the citation metrics. It is not easy to say how we actually measure a scientific success of one project, and we can have more outputs. So not only the citations, what would be nice would be if we had the data to know how many successful PhD students this project had, how careers of the researchers went forward. I think even the qualitative data telling us how satisfied the researchers were during their work at the project is something very relevant. But again, this data was not available, and unfortunately I have impression that even in the peer review or in the general reports about grants, people mainly focus on the publications. And that's also how Fermilab Data Repository was made, right? So they were getting the reports and only picking the publications as a relevant signal of the project success. So there we run into this trouble. And in addition, what is exceptionally important for us is to know that we cannot just compare different fields. Just like a super simple example, a very impactful paper in philosophy will have far less citations than a very impactful paper in biology. And we are aware of that. There are certain studies published where people just compare cross disciplines, all the data and all the efficiency. And if something like that would be done in practice, that could cause huge problem for humanities. On top of that, we are also aware that there is a strong replication crisis, so that even some papers that are not replicable, or even some retracted papers, get a large number of citations, meaning that citations are not always a reliable measure of the scientific success. And there it is then a very big and open question, which raises both the ethical and epistemic concern, which data should be used if such approaches once start being implemented. In physics, we are a little bit lucky, because the field of high energy physics is converging to the results. So the consensus in the field is reached relatively fast and relatively reliable. Of course, there are also exceptions there. And so the field, why is that happening, is because the field follows certain regular inductive behaviors. So they can somehow predict also what will be a fruitful product in their field. My assumption is that in the fields that are less developed or less regular, we could have far more problems with this. Additional and extremely important questions arise with data and are relevant for the epistemic consideration. One is that we cannot really capture so easily outliers using algorithmic grant review. Again, if we would maybe have enough number of outliers, certain tendencies could be captured. But again, the outliers would be a problem, because my impression is that what the signal that we measured here, which gave this moderately high accuracy, is actually something that Kuhn would call normal science. So we can predict something in the domain of normal science, but can we really predict something that will cause the scientific revolution using such methods? I think that's rather hard, but it's an open question, of course, for further considerations. Moreover, we are having unobservable variables that are influencing the success of a project, such as the motivation of researchers. And that is really important, and that peer reviewers can assess in the interview phase, for instance, or what is the team cohesion, which is again something that peer reviewers can observe better, especially in the interaction or in reading. I mean, there are some ways how algorithms could do it, right? So algorithms could see whether there were some previous collaboration, some preparatory work of the researchers on the project, whether they published together. Then there are also these much more spookier ideas that the algorithm can even assess the you know, this eye tracking mechanisms that can assess certain enthusiasm of people and focus and motivation. But that is very, very dubious in my opinion. We don't know what future brings, but it's definitely something that we should be very wary of. And we noticed that there is a potential predictability of the results. We have to be careful that there is no adversarial behavior in these settings, and only compare the parameters in a meaningful way. So only compare projects that are comparable to each other. Otherwise, some type of projects will get discriminated and unjustly discriminated. There are certain ways from the technical perspective how one can amend this situation. So one can add always more and more data to the model. One can include different type of qualitative assessments in the algorithm. So peer reviewers' assessment can be also integrated as one parameter in the algorithm, right? That algorithm will use. And what would be particularly interesting is to see whether we can get some robustness results using different methods that would also point out that these team structures are meaningful for the scientific success, or that researchers evaluating others also value such parameters, or the researchers working on projects with similar structures are more satisfied than the ones working on different structures. So those are open questions that we now formed across national collaboration and hope to explore in the next years. To emphasize more the importance of the field-wise organization of the data is this lesson that we know the data doesn't mean the same in every field. So what is the well-known paper in one field is not the same as a well-known paper in another field with respect to citations. So this impact classification of citation numbers has to be done field-wise. And my assumption is that the different tendencies, even relating to the team structures, will apply to different fields. And there, the data curation comes into play as a very important part. So this data curation cannot just be done by agencies without consulting researchers. I think there it's really important to consult someone who really understands the field and can somehow provide us insightful information on which data is comparable and how should we curate it. Only then, of course, algorithmic techniques can be applied, but only that it's meaningfully sorted. In this context, the main epistemic concerns are about careful data curation, but then also about choosing relevant parameters that will tell us which project will be efficient. Just think about some parameters that people might consider and can be harmful even would be the previous institutions where the researcher worked. That might seem harmless, but actually brings the elitist bias in the game. Or we can make it more subtle. So how many successful grants the institution from which the researcher is applying were there in the past? And that might sound harmless, but will actually implicitly again have this elitist bias behind it. So choosing relevant parameters is essential, and thinking about them. And I think the philosophers should help funding bodies that I'm noticing, especially the Volkswagen Stiftung now is expressing a lot of interest in these algorithmic grant review approaches. I think it's really, you tell them, okay, before any of you apply these methods, there are all these considerations that have to be taken into account. And of course, to determine which projects are comparable with each other, that is also something that has to be left to the scientists. To move to the ethical concerns, the biggest ethical concerns, there is a certain interplay, you will notice, between the ethical and epistemic concerns, and we even talk about epistemic responsibility in relation to the ethical responsibility in the context of science, because the ultimate goal of science is to seek knowledge. And the data brings a lot of these concerns, the privacy concern and the concern of damaging someone's career by saying that someone participated in an inefficient project, for instance, or in general, profiling researchers in such a way is potentially very damaging. Of course, these data can be anonymized and can be carefully stored, but it is still questionable whether so the funding agencies can have it, but whether they should use it and whether we should enforce researchers to agree that their data is used in such a way is ethically questionable. And that can influence particularly early career researchers that might not have yet so much of these outputs that are being measured by the algorithms, but might, they are junior researchers that for instance, 2 years don't publish anything, and then in 1 year they publish 15 papers. And this is an exaggeration, but just that you get a flavor. And these people will probably be discriminated by the algorithm, while a peer reviewer might see more potential in a researcher just by assessing the ideas that the researcher has. The big second concern discussed everywhere in the philosophy of AI literature are the algorithmic biases. And we even at the job market know that sure, AI can help us in processing a large number of applications, but AI also can disregard candidates from underrepresented groups. So it can discriminate female applicants for tech positions, and there are also examples of that from the industry. But there are also ways how one amends and makes algorithms more reliable. So in this context, algorithms have a potential to be more objective than peer reviewers, but also potential to do worse than peer reviewers. And I will now switch to an example that I think is analogous to the potential problems that can happen in science. And that was with respect to the evaluation of students in the UK. What happened during COVID, that the UK government decided to use algorithm to grade students instead of the final exams, because final exams couldn't happen in person, and which sounded as maybe an interesting idea, but it caused a lot of problems because this algorithm was not implemented in a responsible way. And some of the reasons for that are that the scores that students got were based on the teacher's evaluation, which makes sense, but also on the previous performance of the school. And there we see that this second parameter is hiding implicit biases towards different type of schools. And there, and then as the end of the results, the good pupils from poorer schools were downgraded by the algorithm, and there were the public complained about it heavily. It was in the newspapers. It was some sort of a scandal, and these grades were dismissed, and only the grades given by the teachers were used in the end. And why I think this is instructive? Well, because we can make the similar scenario in the context of grant review, where we already have the problem with this elitist bias. That if we would use as a parameter the performance of the institution, what I mentioned before, so the numbers of successful projects done at the institution, or the overall ranking of the scientific institution, that can heavily discriminate a researcher who works at a particular institution and is by herself super successful. And there we have to be like really careful. And also this imprudent use of AI comes with the cost that people trust it far less and are far less willing to participate in such projects. So that's also, so for the funding bodies that want to use such methods, it is also much smarter to do them in a responsible, to implement them initially in a responsible way. Otherwise, people will just protest against it, and with a good reason. The ways of debiasing algorithms and for making them less problematic than human peer reviewers would be, of course, to modify the algorithm by putting some affirmative measure, for instance, in the algorithm, but also by improving the training data. So not having biases in the training data, or massaging the training data in such a way that, for instance, the gender is not visible neither as a proxy nor as an explicit parameter, and also to use the relevant parameters and not something that can hide the real thing that we are testing. In this context, doing intervention studies also makes a lot of sense before implementing any of these solutions, to see what exactly will happen with these algorithms and whether there are problems before implementing them in practice. And of course, I mean, what I always like to stress out is that we will have more fair training data if you would increase the general fairness in our society, which is a long-term process, but it's something that has to be kept in mind. So the algorithms are mimicking our biases. They can, of course, increase them, but they can maybe also decrease them if we are careful there. And then I will focus on this concept of affirmative action that's sometimes considered as relevant in the grant review, where the idea there is that certain groups suffer the injustice over a long period of time, and that justifies that a certain affirmative action should be done to improve their position. Another thing is that if one belongs to an underprivileged group in science, this even individual may be needed to put more efforts just to finish, for instance, the PhD, right? And because it was harder for even this individual just to reach this level, and that justifies some type of affirmative action. So if you want to increase, then there are additional arguments. If you want to increase the number of female PIs in tech positions, we should have, like, one argument is we should have the role models of females in such positions and so forth. Of course, this is, and then the hope is that with this matter, in the future, there will be less injustice, and then we won't have to do any of these type of affirmative actions, but just fairly evaluate everybody. Still, affirmative actions are, it's possible to capture them by algorithms. There is a lot of debate in the computer science community about this, but there are technical ways to do something about it. But still, the decision has to come to humans. And because we know that members of the privileged group often feel discriminated by affirmative actions, and sometimes they have a lot of arguments for that, and not every funding agency even does affirmative action specifically because of this reason, so that nobody gets discriminated by it. So the decision whether this should be done is not to the computer scientists, is to the funding bodies. So we always have to have a human in the loop who will make the decisions what we want to achieve. And why we want to achieve it, and whether it's ethically justified before implementing it to scientists. As the epistemic summary from the epistemic perspective of what we now considered, we realized that we need a field-wise organization of data repositories. Collecting data is not such a problem because funding agencies already collect the data. The problem is more that they would have to invest more energy into organizing this data in a proper way. They need to consider that only similar experiments are comparable. For that, we again need a human in a loop, so a researcher that would certify that. We still need to keep in mind that scientific progress is difficult to predict, so that there will be some outliers that cannot just be used, cannot be detected by the algorithmic grant review. The ethical concerns are adversarial behavior, the problem of algorithmic fairness that we have to keep in mind, data privacy of researchers, and potential profiling of researchers. In order to overcome these difficulties, different types of hybrid methods can be considered. We can consider the machine learning as a pre-screening method in grant review. So if there are really large number of applications, just as an initial selection, whether someone satisfies the bare minimum to pass in the next round, machine learning could be used for that. That doesn't sound as harmful as the other proposals. Then, what we briefly mentioned before, we can also integrate the assessment that peer reviewers gave into the algorithm as one of the parameters. So the score that the project got from the reviewers for their motivation for the motivation of the team members could be integrated in the algorithm, and then we can also optimize over that value. More importantly, if our main concern is are the human biases or the biases of the peer reviewers, then we can also, especially a lot of these grant evaluation processes have several stages. So especially if in one stage peer reviewers rejected the paper, but the algorithm gave high scores, sorry, not the paper, the project, but the algorithm gave high scores to the project proposals, we can still let it pass in the next stage. So that would be a corrective mechanism that we want to reduce human biases, because the algorithm is saying, and okay, again, this algorithm has to be carefully constructed that it doesn't mirror the same biases. Then we can say, okay, great, we can give this project a second chance to be evaluated. And finally, there are different ways of how we can combine these two methods and assign them different weights. And that again depends, that is again a decision that a human in the loop has to make. For the future, what we plan to do, and what I think it's really relevant, is to understand which project parameters humans are evaluating as important. Because humans might think that it is very relevant how many PhD students a project will have in comparison to PIs, to principal investigators and postdoctoral researchers. Or humans might evaluate the time spent on the project as more relevant, or so different, or the number of previous citations of the principal investigator, they might think it's more relevant than the number of students and so on. And these things we can learn about these things. And they can even, and we can even apply different type of algorithm, which is a supervised type of a supervised machine learning algorithm, preference learning, and have a model based on that, which will tell us whether the peer reviewers would consider a certain project higher or lower than based on the data that they are getting, based on the choices that they are given. That is very interesting, because it can also tell us whether humans have certain biases there, how they really reason, and if by any chance the results of such a model match the results of a model that's based on epistemic efficiencies, that would be a really interesting robustness result. My prediction is that they won't match, and that we will have a lot of work analyzing why and what is happening exactly there. The reason why I have this hypothesis is because we noticed that peer reviewers don't really, that their assessment don't really strongly correlate with the later citations of the projects. And but again, this is a really open field for future research. And understanding how scientists reason about the use of AI in their evaluation processes is, in my opinion, essential, because they might raise skepticism towards it, and there might be, we have to understand why, if the skepticism is there, why it is there, what is happening with it, how it should be, how should it be reasoned about it, and always be open for updating the measures done by algorithms in science. So we know that AI is increasingly used for obtaining scientific results. There are already some papers written where AI contributed, and I am pretty certain that soon it will even be used for writing grant proposals. And that puts a lot of pressure on the editors in journals, but also on the reviewers and funding bodies. Do we want to solve this by another algorithm? Does that make sense? And I think it does, in a sense that it is efficient, but it also leads us to some very different picture of science that we had until nowadays. And there it's really important to monitor what's happening and to talk to do potential intervention studies, to really talk to researchers, to really see what is happening with these advanced digital solutions in science, and always be open for updating them, for changing them, and even dismissing them, because we don't really know in which directions all of this will go. So it's great that there is moderately high accuracy of this approach, but that is by far not the full picture and cannot tell us what to do in the future. And I think with all these solutions, we have to, like, it's really important to update if something goes wrong, if people are complaining about certain or noticing certain problems with the algorithms that can be caused either by the data or the algorithm design or even by the approach itself. That's really important always to keep track of and keep in mind and to react on. In this context, I see a nice role for philosophy in the future, because philosophy can now really help us to answer the questions that the increasingly digitalized society brings in front of us. And this line of philosophy is strongly engaged with empirical studies, requires also interdisciplinary collaborations with computer scientists, but also with scientists to whom we want to apply any of these methods. And only in such a surrounding we can really make the responsible decisions about the application of AI in science for the future. Thank you so much.